Hello everyone, welcome back to Bamane Pharm Lectures, where we make pharmacy simple. In today's lecture, we are going to continue with freezing point method. We looked at part 1 of freezing point method, and I advise you, if you did not watch part 1, please after this video check it out so that you can get the real foundation of freezing point method. Freezing point method is what we want to analyze today, where we have been given more ingredients. We shall see how we can go about such questions as we looked at part 1. And for those who don't know me, I'm Bamane George, and I am your tutor. Pick up your pen and your pen and the book, and we get started. We have a question here. Today we are going to start specifically with a question, and we shall learn slowly as we move on. Just pay keen attention. Where you don't understand, please don't hesitate to ask in the comment section. I will be happy to help you. How many milligrams each of sodium chloride, butyl hydrochloride are required to prepare certain mils of a 1% solution of butyl hydrochloride isotonic with tears? Remember, we said that making solutions isotonic is very paramount as far as administration of intravenous infusions or injectables is concerned. So we want to see how we can adjust it. We can make this solution isotonic. First of all, we are going to prepare volume of 30 mils. In our part 1, we are simply calculating the percentage required for the adjusting substance. Here we are going to go an extra mile to find out what quantity of sodium chloride is required to adjust such a solution to isotonicity. So I want you to put keen attention as we go through this number. So the first thing, the volume required is 30. But in this case, we are going to use sodium chloride as our adjusting substance, just like we did in part 1. And our main active drug here is the butyl hydrochloride. And they have given us the freezing point depression of the 1% solution of butyl hydrochloride. So the first thing we are going to do is to calculate how much quantity of sodium chloride, how much quantity of butyl hydrochloride is required to render this solution isotonic with blood plasma. So what we are going to do, we are going to begin by doing that. So how are we going to do that? We are going to come and say amount of butyl hydrochloride, which will be equal to, they have given us for a 1%. But remember, we know that when they say 1% from our knowledge of percentage strength or dilution, we mean 1 gram in 100 mils of the solution. So you can decide either to do it from first principle or to use the shortcut. For me, I will use the shortcut. So I would say if 1 gram of butyl hydrochloride is in 1,000 mils of the solution, how about the 30, which is the required volume? So when we try to compute this, we shall get 0.3 grams or 300 milligrams of butyl hydrochloride in this case. So now we need to ascertain how much quantity of sodium chloride is required, because we are using sodium chloride as our adjusting substance in this case. So what we are going to do, we are going to compare the freezing point depression of a 1% solution of dibutyl hydrochloride with the standard, which is the blood plasma. But remember, we say that blood plasma freezes at 0.52 degrees C. But the temperature at which dibutyl hydrochloride freezes is 0.08 degrees C. So we are going to have a comparison between the two. For a solution to be isotonic, we must have a freezing point depression of 0.52. But what we have at hand is 0.08 degrees Celsius. So that means that we need to find always adjust this solution to isotonicity using sodium chloride. So when you compare these two, you realize that dibutyl hydrochloride is less than the one required to make the solution isotonic. So that means that the remainder will be provided by the isotonic modifier, which in this case is sodium chloride. So we shall get the required freezing point depression of sodium chloride, which in this case it is our isotonicity modifier. So this will be 0.52 minus 0.08. And when you compute this, we shall get 0.44 degrees C. So this is the freezing point depression that is required to render this solution isotonic for sodium chloride. So it means when we add 0.44 to this, we shall get 0.52. Meaning this is the remainder that should be provided with the isotonicity modifier, which in this case is sodium chloride. So after getting this, remember from our previous knowledge, we know that 1% solution of sodium chloride produces a freezing point depression of 0.576 degrees C. So after realizing that this is a freezing point depression for a 1% solution of sodium chloride, but we need to know what percentage of sodium chloride is produces this freezing point depression in other words. So we shall say from first principle that if 0.576 degrees C is the freezing point depression produced by a 1% solution of sodium chloride, how about the remainder, the required that provides the isotonicity modifier? So the 0.44 degrees C will be produced by the 1% divided by the freezing point depression of the 1% sodium chloride being multiplied by our remainder, which provides us the freezing point depression of the isotonicity modifier. And when you multiply this, you realize that we are going to have 0.76% weight in volume solution of sodium chloride. So this is the percentage of sodium chloride that is required. But our question is very clear. They want us to calculate how many milligrams each of sodium chloride and dibutyl chloride which are required to make this solution isotonic. And we are preparing certain moles of that solution. So that means that after obtaining this, we are going to get the amount of sodium chloride. So amount of sodium chloride will be its percentage. But remember, this percentage simply means that we have 0.76 grams of sodium chloride in 100 ml of the solution or water. So we shall say 0.76 is in 100. How about the 30, which is the required? And when we compute this, we are going to get 0.23 grams of sodium chloride. And when we convert this to milligrams, we simply just multiply by 1,000. So we shall have 0.23 times 1,000, which gives us 230 milligrams of sodium chloride. So that means that our final product formula, calling the working formula, will be now, we shall have dibutyl hydrochloride, we shall have the sodium chloride, and now we shall also have the distilled water or water for injection. So this will be, we have got this already as 300 milligrams. We have also obtained the quantity of sodium chloride, which is 230 milligrams. Then water for injection add to 30 mils. And there we shall have made our solution isotonic using sodium chloride as the isotonic modifier. Let us look at our second example. In our second example, they are asking us to compound the following prescription. They have given us atropine sulfate, 1%. They have given us sodium chloride, quantity sufficient. They have given us purified water, add up to 100 mils. Sick, 1 drop in each eye. They have also given us the freezing point depression of the 1% solution of atropine sulfate. Just like we did the first example, you realize that they have given us the freezing point depression of the 1% solution of atropine sulfate. So the first thing always when you adjust the solution to isotonicity is to know the standard. The standard in this case, since we are using freezing point depression method, the standard is the freezing point depression of blood plasma, which is 0.52 degrees C. And what they have given us to atropine sulfate is 0.07. So you realize that when you compare the freezing point depression of the 1% solution of atropine and that of freezing point depression, you come to know that this solution is not isotonic. Because for a solution to be isotonic, it must have a freezing point depression of 0.52. So, since 0.07 is less than this, that means that the remainder, what is remaining to make up 0.52 should be provided with the isotonic modifier, which in this case is the sodium chloride. So that means we are going to get the freezing point depression required for sodium chloride, which is now our isotonic modifier. So this will be the difference between the standard freezing point depression of blood minus that of atropine sulfate. So this minus 0.07, we shall get 0 point. When we subtract this from this, we shall get 5 degrees C. So this is a freezing point depression or the remainder which should be provided by our isotonicity modifier, which in this case it is sodium chloride. So from here we are much aware that the freezing point of a 1% solution of sodium chloride is 0.576 degrees C. So from first principle, since what we need to know first is the percentage of sodium chloride that is required. So that means we are going to say that 0.576 576 degrees C is the freezing point depression caused by 1% solution of sodium chloride. How about the one which we need to make the solution isotonic? It will provide which percentage? So therefore, the 0.45 degrees C will be produced by 1% divided by the freezing point depression of sodium chloride times the freezing point depression, the remainder. And when we compute this, we are going to get something like 0.78% solution of sodium chloride. So this is the percentage of sodium chloride which is required to render this solution isotonic. So what is now our working formula? That means that we shall need to obtain the quantity of sodium chloride in 100 ml of the solution, because this is our formula. But since the formula is up 100, it means that we have 0.78 grams of sodium chloride in 100 ml of the solution. So our working formula is going to be 1. We shall have atropine sulfate. We shall have sodium chloride, then water for injection. Atropine sulfate, it is 1%, because when we say 1 out of 100 times 100, we shall get 1 gram. So we shall have 1 gram of that. Sodium chloride, we shall have 0.78 divided by 100 times 100. We shall still have 0.78 grams. Then water for injection add up to 100 ml. And by doing that, we shall have made our solution isotonic with blood plasma and safe for administration to the patients. Example 3. Our example 3, you're provided with the working formula. They have given us the mass of sodium chloride. They have given us dextrose, quantity sufficient. Distilled water add up to 500 ml. Then they are asking us to make an isotonic solution. That means this time around we are going to use dextrose as our isotonicity modifier in this case. So that means, but we are using freezing point depression as the method. So since we know the mass of sodium chloride, we need first of all to cross-check and see what temperature of freezing point depression is produced by this mass of sodium chloride. Because it is this freezing point depression that will tell us that either our solution is isotonic or it is not isotonic. If it is isotonic, then we don't need to adjust it to isotonicity. But we need to know, is the solution hypotonic, is the solution hypertonic, or it is isotonic. We can only determine that when we ascertain the freezing point depression that can be produced by this mass of sodium chloride. But how do we get that? Remember, we already know the freezing point depression of a 1% solution of sodium chloride. So, since 1% produces this will produce how much? That means, since we are saying 1%, that means that we have to convert this mass into a percentage such that we can create a relationship between the freezing point depression of sodium chloride for a 1% solution. So we shall begin by converting the mass of sodium chloride to percentage, whereby we know by to convert 900 milligrams to percentage, It means we have to convert it to grams per 100 mils. But remember, this mass is in 500 mils. But when we are dealing with freezing point depression, we determine for what is in 100. Because when we say 1% solution of sodium chloride produces this freezing point depression, it means that when we dissolve 1 gram of sodium chloride in 100 mils of water, it produces this freezing point depression. So we want to know, since we are converting to percentage, and you know percentage, it is grams per 100, we shall begin by converting the 900 milligrams to grams. But remember, we know that 1 gram is equal to 1,000 milligrams. So that means that 900 milligrams will be equal to 1 out of 1,000 times 900. And this will give us 0.9 grams of sodium chloride. So after getting the grams of sodium chloride, what is next for us is to convert it into 100. Remember, this one is in 500 mils. So we shall say 0.9 divided by 500 times, this will be times 100. So this will give us 0.18%. So after obtaining the percentage required for this mass, it means now we are going to obtain what temperature can be caused by this percentage. But we already know from our previous examples, we know that 1% solution of sodium chloride produces a freezing point depression of 0.576 degrees C. Now, how about the 0.18%? So, the 0.18% solution of sodium chloride will be produced by 0.576 degrees C divided by 1 times 0.18. And when you compute this, we shall get 0.104 degrees C. So this is the freezing point depression which is produced by the 0.18% of sodium chloride, the one given in the formula. But remember, our main aim is to find out whether this solution is isotonic with blood plasma, hypertonic, or hypo. So in this case, we are going to compare the 0.104 degrees C with the 0.52, which is the standard. And when you bring the two, you realize that 0.104 degrees C is far less than that required for a solution to be isotonic. So that means we are going to adjust our solution to isotonic because from our view, it tells us that the solution is hypotonic. So what happens is, remember they have given us the freezing point depression of 1% solution of dextrose. And the remainder here becomes for our isotonicity modifier. So we are going to say freezing point depression required for dextrose, which is our isotonicity modifier. It means that that will be equal to the 0.52 minus 0.104. And when we compute this, we are going to get something similar to when you compute, we shall have this minus that where we shall have 0.416 degrees C. So this is the freezing point depression. The remainder that should be provided with the adjusting substance, which in this case it is dextrose. But remember, we know from our question, they have said that 0.101 degrees C is a freezing point depression produced by a 1% solution of dextrose. How about the remainder which is required? This will provide 1 divided by the 0.101 times the 0.416, and when you compute this, we shall get 4.12% solution of dextrose. But remember, our aim here is to calculate what quantity of dextrose is required in this case. So we are going to say the quantity required is 500 mils, but this is in 100. So we shall say amount of dextrose in 500 mils. This will be the 4.12 divided by the 100, because when we say percentage, we understand what it means, times 500. When you compute this, we shall get 20.1 approximately as our mass of dextrose in that case. So when we write the final product formula, it will appear to be so our final product formula will be, in this case, or call it the working formula. So this will be sodium chloride, which is 900 milligrams, then dextrose, which dextrose we have obtained as, it is 0.6, sorry, 0.6. So that is 0.6. So when we convert it to milligrams, we shall have 6 milligrams, like that. Then water, distilled water, up to 500 mils. Or you can decide to write them in grams, whereby you can also convert this to 0.9 grams, and this will be our final product formula in this case. Where you don't understand, please raise your concern in the comment section. I'll be right there to help you. Let us look at our fourth example. Our fourth example, you're provided with the following formula: ephedrine hydrochloride 1 gram, chlorobutanol 0.5, sodium chloride quantity sufficient, distilled water add up to 200 mils. They have given us the freezing point depression of 1% solution of both ephedrine and chlorobutanol. Make the solution isotonic. In this case, we have 2 ingredients. So that means we are going to begin by, we are going to get the total freezing point depression of the 2. Then we compare the total freezing point depression of the 2 with the standard, which is 0.52. Then from there, we shall go slowly, like we have done in our previous examples, and we obtain the answer. This is your official assignment. I want you to pick up your calculator and your pen and try it out, and you drop your comment with your answer in the comment section down there. I'll be right back to tell you whether you got it right. And if you have not yet subscribed to our channel, please subscribe to the channel to keep it growing and also keep you updated with more simplified pharmacy calculations. And also, if you have any question or any topic you want us to cover next, feel free to raise it in the comment section. I'll be right to help you. Like the channel, leave a like, turn on your notification button to keep you updated with more videos that are coming up. Let's catch up in the next lecture, and don't forget to share the channel with your other colleagues who may also find it very useful. Thank you for watching.